Okay, last projectile problem in the slides. Tennis player hits a ball 2 meters above the ground. The ball leaves her racket with a speed of 20 meters per second at an angle of 5 degrees above the horizontal. The horizontal distance to the net is 7 meters, and the net is 1 meter high. Does the ball clear the net? If so, by how much? And if not, by how much does it miss? Okay, so let's draw our picture. So we have a ball getting hit. Okay, and it's starting at a height of 2 meters. And it's hit just at a small angle, that's really even too much, 5 degrees above the horizontal with a speed of 20 meters per second. And then it's got to travel 7 meters to the net, and the net is 1 meter high. And the question is, does it hit it, right? So is it kind of clearing it like that, or maybe it goes down too fast and it hits the net? So we want to know basically what is y final. Okay, so let's list what we're given here in the x direction. I'm going to put my coordinate right where the ball is hit, down at ground level. So this is plus x, and that is plus y. Okay, and we have our initial x, our final x, our v0x, and our ax. X initial is 0. X final, I forgot to put it in there, is going to be 7 meters. Our initial x, right, we have a velocity at an angle. So here's v0. Okay, and there's theta. And here's v0x and v0y. So I can do my trig function. So I'll start with sine is the opposite side over the hypotenuse. Sine theta is v0y over v0. So v0y is v0 sine theta. Cos theta is v0x over v0. Solving for v0x, I get v0 cos theta. Okay, and then y. Okay, so v0x, I'm just going to put in here v0 cos theta. If I plug that in, so it's 20 meters per second times the cosine of 5 degrees. I calculated that already just to save us some time. And what did I get? I think it's 19. No, this is a small part. It's 19, yeah. Mostly it's just in the x direction. Okay, 19.92 meters per second. Yeah, because my y component would be really small for a 5-degree angle. And then v0y is going to be 1.74 meters per second. Okay, so we could actually put it in here, 19.92. Acceleration of the y is 0, and then we have y0, y final, v0y, and ay. Y0 is 2. We don't know what y final is, but we're going to compare it to the 1 meter net. Our initial y velocity is 1.74 meters per second, and our acceleration is negative 9.8 meters per second squared. And we want to find y final. Okay, so if we don't know where to start, we can write down our equations for the x and y directions. So x final is x initial plus v0 xt plus 1/2 ax t squared. And then we can do y final is y initial plus v0 yt plus 1/2 ay t squared. Okay, so let's look at our list. X initial is 0, that goes away. Ax is 0, so that goes away. So x final is v0x times t. And then in the y direction, pretty much nothing is 0. This is what we want to find. We do know this. Y0, we know v0y, we know ay, we don't know t. So we're going to use our x equation because we know v0x and x final, and we can solve for t. So let's circle that. So T equals x final over V0y. And that is 7 meters. V0x, and V0x is 19.92 meters per second. So sometimes I'll just leave this as a variable and plug in, but it's a little bit complicated, so let's just solve for time. So it is, I got 0.35 seconds. Let me see if I can get that a little more, one more significant figure, 0.351, okay. Okay, and now we can go to our y equation and solve for y final. So y final, plug in our values, is y initial, so that's 2 meters. B0y is 1.74 meters per second times our time, 0.351 seconds. And then 1/2 a, so that's minus 4.9 meters per second squared, and then 0.35 seconds squared. Okay, running out of room a little bit. Okay, and if I put that into my Python or your calculator, I get that y final is 2.001, let's say, meters. Let me just check that again. 1.7 times 0.35 minus 1/2 a t squared, yep, 2.01. So, yes, it clears the net, okay, because the net was only 1 meter high, and it's saying it's right about at 2 meters again, kind of right where it took off. So it's gone up and come back down again, and then it will keep going over. So it clears the net and by 1 meter. Yay, the last projectile problem. Woohoo!